And yeah, then okay, right. So let me just summarize things for you. The main takeaway for us here is that we are learning certain new sort of, I would say, yeah, new ways of uh, proving things, and also, like having some mathematical terminology to talk about games. That those were some of the things which we have learned so far. Right? So we were looking at just a summary of what we have done so far is we were doing this games on graphs. Right? So again, the place where we're playing the game is a graph. Okay. So G was a graph, and we partitioned G into two sets. Right. Yeah, we partitioned G, the vertex set of G into two sets, V0 and V1. And yeah, and obviously the edges are always there. So this kind of graph, again, maybe I've not used this term before, but this is called a game graph. Okay. Or maybe, yeah, game graph is defined as game graph. Okay. Our games were infinite. We had two players, right? And if we imagine that we had a token, and now if the token is at the vertex of player 0, then player 0 makes a move, and similarly. And then, so basically a game then became an infinite sequence, right? So that was there. And after that, we have to really say when we have a game like what is the definition of winning or what is the definition of losing, right? So for that we had a payoff function, and since we basically were talking about qualitative, in the end you could say Boolean qualitative games. So the payoff function that we had, payoff function that we had, that was a function from basically for every run of the game. So this is infinite product, right? To 0 comma 1, right? To 0 comma 1. And right, and this payoff function was pi, right? And then we can basically define winning or losing in terms of this payoff function. So we would say that a run of the game is winning for player 1 if the payoff function returns 1, right? And so on. So now, so that's the summary of the general setup. But now let us come to this reachability, the problem that we were doing. So we were looking at a special type of game, which was reachability games. So we saw an algorithm for this basically, but and today maybe we'll see a very small variant of this, okay, and then we will do the repeated reachability. But can you tell me what this repeated, sorry, what this reachability games was about? Maybe in this terminology,
So,
if possible.
like we want to reach some subset T of the graph.
Right. So
Like
T,
that is what a player is playing for.
right, that's what player 1 is playing for, right?
Yes.
Yeah. So that's right. So player 1 is playing for reaching the vertex V. And so from this, what should be the payoff function? Because that only mathematically, that only will say, right, what you are declaring as winning and what you're declaring as losing.
So the payoff function should be uh, so the payoff function to. So I didn't understand the question actually.
Right. So suppose that I have this infinite, suppose a run of we run the game. Okay.
Yes.
And then that gives us an infinite sequence. Okay. Now, when should this go to 1? What
Oh,
should be the
okay. It should go
reach?
to
Hmm.
1 when some vi for some natural number I or whole number I belongs to T.
Exactly, right. So this
Yes,
goes
sir.
to 1 if and only if there exists a I greater than equal to 0 such that Vi is equal Vi belongs to T. Perfect. Correct. So this is it. This because this way we are encoding that thing that the player 1 is playing to win. Right. Okay. So now
Yes, sir.
the question. So this is the we are declared selling what the game is and what the payoff function is. Now the question really is, and some terminology is there, but now the question really is, uh, find win let's just say it like this because we have talked about this. Find win one of G, meaning find those vertices, yeah, such that if the game starts from there, so that if V naught is equal to that vertex, then there is a strategy such that if player one follows that strategy, then no matter what strategy player zero follows, the output will be one, right? So this was about finding win one, right? So we have an algorithm for this, right? So we have a positional strategy, in fact, positional strategy uh, for these vertices, and also an algorithm to determine these vertices. Okay. So we know how to find these vertices in the graph, right? You start with the vertices of T, and then we expanded that set, and eventually we saw that that's exactly the vertices that we get. We proved that are exactly the vertices from which player one will have a strategy. And what will that strategy be? That's also very clear from the way we got those vertices. Right? Like if you are right. I mean, yeah. So yeah, it's yeah. So if you find that vertex V in Win1 at the ith stage in that iteration, then you know what he should do, right? If he yeah, that's fine. That was in there. So we don't need to go into that now. But what I am interested in is this other question, and let us see if we can now we assume that this can be done. We assume that we have done this. Now, can we use this? That is the question. Now I will define what is called a safety game. Okay. Now things will be easy to define. And let us see if you can figure out the safety vertices and so on. So, what will the safety game be about? So, let me see. Right. So now we will just have a set of vertices called safe vertices. Okay. And the yeah. So we will say player one wins. Okay. If pi goes to one. Yeah. If pi maps to one. Yeah. Yeah. One wins if game is in pi inverse one. Okay. What is pi? We have to describe. So pi of a run is equal to 1 if and only if Vi is in S for all I in N natural numbers and obviously including 0. Okay. So here you understand in verbal terms what this means,
Yes, sir.
right? This just means
Yes,
that
sir.
player one wants always to remain in S, right? So, can you think now what will be the winning vertices? Now, in this case, what will the winning vertices be? So, what are those vertices that such that if player one starts from there, then he can ensure that he always stays in S, right? Because that's the criteria for winning. And the hint is that you really don't have to do anything for this. You have to just invoke the previous situation. It's just a test in whether you can apply the previous one by just a little bit of a set theoretically switching the things. Just think about this for a little bit. Or you can come up from scratch
Yes.
also if you want. You can come up with something.
Y- Yes, I'm thinking. So is it just S?
Um, it's not even clear that it will be S, right? So you can take an example, right? So suppose that this is in S, right? But uh, so suppose that this is in S and this is in S. S is not S itself may not be a safe set. This is S. But what if all the edges from S are outside S? Then it's by no means safe, right? That set may be empty also. This win1G may be empty also. Like, is this safe? No. Is S safe? No.
N- no, because the edges are leading out.
Outside. And so there's no way, like, yeah, to stay inside S. You can think completely in verbal terms, even without the technicality, and see how it is related to the previous question.
So isn't it like the set of all vertices uh that have edges that lead into S?
Okay, so those vertices, okay, so you are saying that's no, but then again, right, after going inside S, you may not remain to stay in S. You may come out. Just with what you are saying, you may come out again. Right? You don't want to come out. So suppose that this is in S, this point is in S. and this is outside. And let us say that this vertex V belongs to player 0, right? So player 0 doesn't want to go in S, but even then, let's say this is the only edge, so it goes in S, right? But again, if this vertex W again belongs to player 0, okay, if this vertex W again belongs to player 0, and if there is an edge that goes outside, then he will by all means go out again, right? So then, then this W is not a safe set, right? So like after all, right, after that point, everything has to remain in S. All the moves have to remain in S, right? If this W belongs to player 1, then it is reasonable that he will take this edge, okay, and he will remain in S. And let's say this again belongs to player 1, then, and if again there is an edge like this, then again he will go back and they'll cycle and always remain in S. But if that happens, so you cannot say for sure from your condition. The condition you give, that itself doesn't imply.
So then I'm not sure, but like maybe like yeah, I'm not sure, so I'm not getting
Right.
for some
So
reason.
it's okay because this is the new kind of problem, right? That was what we did was like the part A of a very new kind of problem. It's simple, but it's new to you. And this part B is like part B of that question, but you have to simply apply part A. So think in that direction. So a lot of times it is like that, okay, that you have to, some new things will be introduced, you have to get comfortable with it and you have to solve it. But that solving will actually not be anything novel. That solution will not be anything novel. You have to just apply the thing that's already given. So let's go back to this reachability problem, okay. Now, if you look at this win1g, so win1g is something that we have calculated, but also in uh, yeah, in the process we also got win0g, right? Which is nothing but the complement of win1. Okay? These are the vertices from where uh, player 0 has a strategy of never reaching T, never letting the game reach T, no matter what player 1 does. Do you agree?
Yes, sir.
Right? Because it's just a complement, right? Yeah. So now if you look at win0g, and now if you look at v minus t, so look at these vertices and yeah, look at these vertices, win0g, and look at these vertices, okay? Now do you see a connection with the previous problem? Starting from here, so if there is a vertex which is in win0g, then player 0 has a strategy using which he will always remain in V minus T by definition. He will never let the game reach T, but that just means he always remains in V minus T.
Yeah, yes, sir.
Now you can see this is exactly the question which was asked, which
Right,
was just
right, right.
asked. But obviously that was just a little like player 1. So you have to switch. And this is the thing, strategy you may give the strategy to player 0, you may give the strategy to player 1. This application of it, like dealing with these things, like we deal with functions and substitution of variables and those, that's the level of flexibility one needs. So this is like the safe set, right? And yeah, so let's say that if this was the given safe set, then this win0g, right, is basically the winning set for S for player 0, I should say, for player 0 for the safety game. Sounds very bad but yeah. Let's write it better maybe. For the safety game, right? So basically the solution is of the safety game is in the reachability game only. Right? So if S was the starting set and you had to find the safety vertices for player 0. Okay, so the goal of player 0 was to remain in S. Then what you can just do is you can take the complement of S, right, and play the reachability game for player 1. Right? Then the vertices that you get would be reachability vertices for player 1 in S complement.
Okay, yeah, I get it.
Yeah,
So you go outside of S and treat it as a reachability game where you want to reach S.
yeah, reachability game for 1. Like 1 wants
Yeah,
to
for
reach
player
that.
one.
Right.
Yeah,
And
yeah.
right. And now let us just write this properly because this is just said in words. This can actually, when you write it, may actually confuse more. It will not by all, I hope, but let's write it for, yeah. So you see how now you can sort of feel how, this terminology is useful in transforming, using one thing, copy pasting nicely, easily. Yeah. So for finding win1g, what we should do is we can look at. So what is win1g? So maybe let's write it in steps, then it is easy. Step 1 is S is given to you, right? So you take this, right? Take this. And step 2 is uh, play reachability for player 0. Yeah. Player 0 wants to reach B minus S with, like, the most of the times one doesn't have to translate everything in verbal language because this language itself is convenient, but still, yeah, it's if you need to, you translate. Player 0 with V minus S, or maybe with, I should in fact say with T equal to V minus S. T equal to V minus S. Okay. Step 3, the win 1G, and maybe I should say win 1 of this safety game. This is, because now there are 2 games going on, right? So I should mention it is win 1. This is equal to, um, just a second,
So
okay.
win zero reachability
Yes, I
G
do.
complement.
Yes, I do want to write that, but okay, let's write it.
It's a bit long.
But yeah, some consistency problem is there with where we have used win 0 earlier. But we will rectify that. Let's first write this with this V minus S with this T. Okay, right. Yeah. So yeah, so we're starting with T. You find out all the vertices from which player 0 can always reach T, and no, wait, yeah, player 0 can always reach T. Yeah, this should take a complement, right? Yeah, we have to take a complement.
Yeah, complement of the same thing.
Yeah, so V minus this, right? Yeah, because those are the vertices. Win 0 reachability T is the vertices from which player 0 can always reach T, right? And if we take the complement, then then in those, so if you take a vertex in the complement, then player 1 always has a strategy to never let the game reach in T, which means he'll always put the game in S. And so that's the safety, right? Yeah, right. So this is correct. Only that the way we have um used win 0 in reachability was that player 0 doesn't want to reach T. That was the sense in which we had used win 0 there, right? And But here we don't want to say that. I mean, it's fine. It's if you write it in words, you can just write in words what this means, and then it is fine. But if you don't want to write the words and just want to change some notations, then let us see. Yeah. So win one safety. Hmm. Yeah. So here I can say that you can swap player 0 with player 1, right? Here I will say that you swap player 0 with player 1. Okay. And uh, yeah, but then also it's a bit confusing. Anyway, so you can just write it in words. It's not a problem. Okay. Yeah, you can just define what win 0 means in this case, write the words, and then it is fine. Yeah. All right. Basically, but we get the solution, right? So it's just I think it's interesting. It's a interesting application of one thing which we did. Okay. So now we should try to do the repeated reachability. So how much time do we have? It's 8:10, which means yeah. Yeah, so let's take a break and then we do the repeated reachability on the other side. Let me just mention the problem. Maybe you should think about it meanwhile. Yeah, that's what you should do. So here I'll just mention it in words now. Okay. First. First we'll mention it in words while doing. So now we have a target set T. Okay. We want to again reach there, but now we want to find those vertices. Okay. V naught such that player one or let's say we are player one, we have a strategy to which we have a strategy starting from V naught, we have a strategy which allows us to reach the target set T, some vertex in target set T again and again. Okay,
Again, so again and again, as in.
infinitely often, right?
Okay,
Okay,
infinitely often.
yeah.
Okay.
So again, you understand what the payoff function where it will go to one. Only those will go to one where Vi is equal to T for no for I infinitely many i's. Okay,
Infinitely many eyes. Yes,
which
sir.
you can also say that like for any j there is a I such that Vi is bigger than Vi is inside T, like a subsequence. Yeah. Yeah.
Yeah.
So
Yes, sir.
yes, that's the kind of thing. I mean, so certainly you can see that again, if you play the safety game, right, then what was returned by the safety game will certainly be in this. Am I correct? Yeah, right. Win one safety of T. If you treat T as a safety vertex, no. So you take T and you put it in the safety game. You call the safety game with T as a safety set, and player one is trying to win. Then the vertices that are returned, those will certainly be winning, right? But will they be all? I don't think so. Right? They will be winning because from those vertices, player one has a strategy to always end up in T, like to remain in T forever after some, right? So yeah, yeah. So they are certainly there, right? To always remain in T. Yeah, even eventual safety, but that we don't have an algorithm for because we don't have algorithm for repeated reachability. But yeah, safety set would be there, but that will be too small. That will not be the whole. There will be other vertices which are not safety, which means that for starting from there, player one cannot ensure to always remain in T. But it may still be possible that he goes in T once in a while, at 2th stage, then 4th stage, then 8, then 16, but he still goes. So yeah, think about it. This is a little tricky question. Yeah. Right.
Yes, sir.
So remember, we have to figure out those vertices from which this is possible. Okay. Yeah.
Okay. Yes,
Right.
sir.
Okay. Just like earlier, we figured out the vertices from which it was possible to reach T only once, but to reach. But now we need more. All right, so let us think. Yeah.